Yo, Joes. Some of you may be saying, 3 videos? Really? Yeah. I don't have work until later, so I figured that I would more or less finish up to the section that I wanted to. So, in my last couple of videos, we did the problems and gone through a bit of a tutorial of chapters 2.1 and chapters 2.2 of Schroeder's book on thermodynamics, and so we're now hitting that point in the discussion where we talk about Einstein solids, and eventually what Einstein solids are supposed to do is get us to the point where we're having a discussion about entropy and the second law of thermodynamics. First and foremost, what is an Einstein solid? Well, an Einstein solid, as the board states, are solids described by a system of quantum mechanical, that's what the QM stands for, harmonic oscillators. And, excuse me, quantum mechanical or quantum mechanical harmonic oscillators are very similar. Will have a potential function of kr squared have a potential function by their position squared, and if we talk about what that means is there's a solution. Well, these harmonic oscillators have a solution for the Schrodinger's equation such that their energy their energy levels are discrete. And these discrete energy levels, if you have any background in quantum mechanics, these discrete energy levels are separated by an integer, and this integer is to represent but these integers, or the total energy of the system, E sub n plus 1. This energy is to represent individual photons or levels within the harmonic oscillator in which the electron is available to occupy. And you're seeing me move a lot. One, because I'm a bit uncomfortable right now talking about quantum mechanics, because depending on the level of the viewer, depending on the level of the viewer, and one, how early it is in the morning for me, you may not fully appreciate what it means, this statement anyway. So let me give you a bit of a visual. So in one dimension, if you only look at this potential and the solution of the Schrodinger's equation in one dimension, electrons can only occupy units of energy of each bar f, and well, units of energy with a difference of h bar f. So the difference between the energy level here, which is your first rung, or your first available energy level, where n is 0, actually, yes, where n is 0, and then when your energy level is n is 1, when you actually get to the next available energy space, you can only have a discrete amount of energy added to the electron or taken away from the electron in order to move it up and down this sort of quantum mechanical ladder, if you will. And actually that gives us a very simplistic model for dealing with energy and counting. And I'll show you in a moment exactly how counting helps, or how counting is involved, such that, where we dealt with the coin being an independent state, these various quanta are also independent energy levels for each individual oscillator. Let's take a step back. And, well, let's not take a step back, but let's take one forward. And let's do a bit of an example. Because I feel like I not only explain things a little bit better through example, but also some topics like these are a little bit better or more understandable through example. We know that each energy, or each photon, really it's phonons, are have a discrete energy level of at least 1/2 h bar f. Forget the n for a second. We say that we're at the 0-point energy level. We can only add a phonon of h bar f, or q. Schroeder uses q, or at least an integer level of q, to the system, to a harmonic oscillator, to excite the electron one level upwards. We know that we can only do that. So we don't really have to write out too much information. We can really use basic integers, but remember what these basic integers, q, are meant to represent. Q is to represent units of energy. And so let's start from there. We have a single harmonic oscillator. And this single harmonic oscillator has available to it 2 units of energy. What is the multiplicity of that system? Okay. All right, Robert, we're following you. I think that's a bit too easy, but we're following you. So let's write down oscillators. One oscillator and 2 units. That's it. It's pretty boring. But say we have 3 oscillators and we only have 2 units of energy available to the system. How many different ways can we express 2 units of energy and 3 oscillators? This is where things start to get a little bit more interesting. So if we put the 2 units of energy on the second oscillator, that's possible. We could also do the same thing for the third. Okay. So we distribute the units of energy. Is that all of them? Yes, actually. Because we can't have any fewer, or we can't break down units of energy outside of integers. Remember that n? N must be an integer. N can't be a half integer. So we can't have half of an energy unit here, half of an energy unit here, and then a whole energy unit there. The multiplicity of the system of 2 energy units with 3 oscillators is 1, 2, 3, 4, 5, 6. And so let's say we're given 3 energy units. Well, we should have a greater multiplicity. Shouldn't have erased those. Let's say 3 energy units, so 3, 0, 0, 0, 3, 0, 0, 0, 3. Then let's say we get 2, 1, 0, 0, 2, 1, 0, 1, 2, 1, 2, 0. Is that all? And then 1, 1, 1. Of course, 1, 1, 1. 1, 0, 2. 2, 0, 1. I think that's all of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a multiplicity of 9. And so the way that we're given this, or at least the formula for determining the multiplicity, is given as the following. Omega, favorite letter, n cubed equals q plus n minus 1 q. And if you remember the formula for the basic combination formula, you get q plus n minus 1 factorial, q factorial, n minus 1 factorial. Excuse me. And so let's see if this works. So we had 3 units of energy, 3 oscillators, minus 1. So this is 5. 5, 3. This has to be 5. 3 factorial. 2 factorial. Well, 5 factorial. 5 and 4 is 20, 23 is 60, 120. 120 divided by 6. 120 divided by 6 times 2, which is 12. This has to be equal to 10. This has to be a multiplicity of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I missed one. Which one did I miss? 2 up front, 0, 1. Alright, we got that one. 2 in the middle, 0, 1. 1, 0. Ah, that's what it was. 2 in the middle, 1, 0. Multiplicity of 10. We got them all. Nope. That's this one. That's a copy. Nope, 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 nope. Before you ever do that, make sure that you verify all your work. 3, 6, 9. So which one did we miss? Yeah. 5 factorial, 3 factorial. Huh. So we got all the 3's. This is 3. 1 in the center, 2 on the left, 0 on the right. 1 in the center, 2 on the right, 0 on the left. That works. 2 in the center, 0 on the left, 1 on the right. 1 on the left, 0 on the right, so that knocks those out. What about 0 in the center? Yeah, 0 in the center, 2 on the right, 1 on the left. That's the one that we forgot. Yeah. Yep, that's the one we forgot. So this is the complete set of the multiplicity of Q equals 3 and 3 oscillators. So the question is, well, okay. So this uses the the multiplicity stuff that we've been doing with coins and things, but how does this push us forward? Well, this will eventually help us, like I said, understand entropy a little bit better once we get to that point. Because now we're talking about physical objects. We're talking about solids that, well, really Einstein solids are a toy model for solids. And talking about physical objects in the sense of quantum harmonic oscillators with energy units, which are technically phonons, but we look at them as photons because of how we describe the energy and how we look at quantized energy. But we're looking at real things right now, as opposed coins are real things, but we're looking at real physics things, as opposed to just counting numbers. And this formula it's different from what we looked at before, even though the form is the same. Look at how we're subtracting by n. Look how we're subtracting by 1. Look at how we're counting how the energy is moving. And the reason why we're subtracting by 1 is because how we're counting out these units of energy. The system can't have a 2, 0, 0. It can't have a 2, 0, 0 because we have 3 units of energy in the system. Not just available to the system, but in the system. We're counting the oscillators for units of energy of 3 distributed. In reality, you do have the probability of getting 3 harmonic oscillators with 3 units of energy available and only distributing 2. You have a very small probability of that occurring, but that probability is practically 0. You typically have all the energy available to the system distributed into the system. You usually don't have any, don't have, for solids like this, you won't have any like reflections and then 2 units of energy are in the system and then only 2 oscillators are doing that. It also depends on the types of solids that you're dealing with. But yeah, let's deal with some problems. And don't worry, we'll talk more about what Einstein solids are, and talk more about how we use them in terms of like in greater and more sophisticated physics. Not greater, but yeah, more sophisticated physics examples. So we have. So in problem 2.5, excuse me, I'm really sorry guys, I'm also getting over a flu, and so I'm doing these videos for one, doing all of them today, for one, because I have the time to, but for two, well, I have the time, and if you remember my first video, This is my training time, so I've already dedicated the time to do it. But more importantly, what was I getting the point? I was getting over a flu. Oh well. Forget my point. Anyway, problem 2.5. So problem 2.5 gives us a list of oscillators and a list of energy units available to the system, and it just asks us to find, what's the multiplicity of the possible microstates, or you can list all the possible microstates, but I feel like the multiplicity is a little bit better suited for the problem. I will list one of the multiplicity, but I won't do all of them. I'll do the first one though. Some of them can be a bit long. Excuse me. So you've got three oscillators. You got oscillators 1, 2, 3. You have a total of Q equals 4 energy units available to the system. How do these 4 energy units distribute amongst, or how many different distinct possible ways do the units of energy distribute amongst the oscillators? And the answer is, list them out. 4, 0, 0, 0, 4, 0. Don't want to be here all day, Robert. 0, 0, 4. 1, 3, 0, 0, 3, 1, 3, 1, 0, 3, 0, 1. 1, 3, 0, 3, 1, 0. Now we go to the 2s. 2, 2, 0, 2, 0, 2, 0, 2, 2. Is that it? I think so. 2 1s. 2, 1, 1. 1, 2, 1. 1, 1, 2. Is that? Yeah, I think so. You get 0, 3, 1, 0, 0. This is it. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Came up with 15. How many did I come here with? Yes. I got them all. Jesus. So, easy. Now, how do we confirm? We confirm with the formula. We see if if we got the number correct. 3, 4. If you remember what the formula is, Q plus N, so you get 4 plus 3 minus 1 factorial, Q factorial, 4 factorial, divided by N minus 1 factorial, which is 3 minus 1 factorial, which is 2. This gives you 7, 6 factorial over 4 factorial, 2 factorial. 15, baby. And so the other ones are literally just the same thing. But let's go back to that one oscillator such circumstance that I brought up before. How many different ways, if we only had one oscillator, could we do 4 units of energy to the system? Well, 1. You can only have it one way. You could only have that one oscillator have all 4 units of energy to it. So what about 5 units of energy? Well, 1 and 5. Let's put it in this formula. 1. And let's not give a number. Let's give it Q. Okay. This confirms exactly what I just said. You can only have it one way. If you have one oscillator and you have, any number, Q number of energy units available or in this pumped into the system, you only have a multiplicity of one. You only have one possible state. You don't have 1 and 0. You do have you have a very slim chance, in reality, a very slim chance of having 3, 2, 1, or 0 units of energy in the system, where you have the system in the 0 state, 0 in the 0 energy state. But those probabilities are very slim. This is 1. So if we have 30 oscillators and 30 units of energy, what's the multiplicity of it? It's a huge number, because this is going to be 59 factorial, 30 factorial, 29 factorial. It's a big number, and you definitely don't want to list off the microstates in that circumstance. So as the number increases, especially the number of oscillators increase. If you have a small number of units of energy, you don't have to worry too much. But if you have a large number of oscillators, you start dealing with some really humongous numbers. Because if you think about it, say that this was 3,000 and this was only 1, well, still got a 3,000 factorial in the numerator and a 2,900 factorial in the denominator. Well, the answer is 3,000. You have 3,000 different microstates. So it's not so bad. It's when you start dealing with, I guess, yeah, it's not so bad if you have a small number of units of energy. And again, if you think about it, only 1 unit of energy, therefore you'd have to have 1 unit in all 3,000 spots, which then if you make it a matrix, it's a diagonal matrix. It's when you start dealing with numbers that start getting bigger and bigger and bigger. I guess both would have to, increase relatively largely. 30 and 30 is a huge number. 30 factorial, 30 factorial. No, this is 59 factorial, 30 factorial, 29 factorial. So it's pretty bad. It's manageable, but it's pretty bad. 10 to the 10th oscillators for humongous solids. You start dealing with tremendously large numbers, and just avoid them. We'll deal with ways of dealing with large numbers and multiplicity in just a moment. That's more so section 2.4 and section 2.5, where we start dealing with Stirling approximations. But for right now, that's more or less all I wanted to really say about Einstein solids and their problems. Next section that we have are interacting systems. Interacting systems. Interacting systems are just where you have 2 solids and how they interact with one another and distribute energy amongst one another. That's Thermodynamics 101. And folks, finally we get to actually start talking about that stuff. Stuff that's less basic, less counting, and more science. Thanks for watching, thanks for stopping by, and I'm starting to like these 29-minute videos. We'll start trying to limit ourselves to 30 minutes. Sounds great. Bye-bye. Stay tuned. I will be getting the electrodynamics videos up today. Bye-bye.